Okay, so it should be page number 11. We're going to finish off lesson 7.2, looking at the graphs of exponential functions. So on the diploma exam, on the formula sheet, there is a formula given for exponential growth and decay. And that formula is y equals a times b to the power t over t. That's the formula that is on the formula sheet. Okay, so b is the base, and what we've seen before, that if something is doubling, the base will be 2. If something is tripling, the base will be 3. If something's being cut in half, and in those situations they'll talk about a half-life, then the base will be a half. So the base is the multiplication factor. And then the exponent, as we see here, is divided into 2 parts. T is the time that is elapsed. Okay? How long has this been going on? And P will refer to the doubling period or half-life period. And you just have to make sure that these two are in the same units. Okay? So we'll go through some examples and see how this formula is used. This first example says a cup of water is heated to 100 degrees Celsius and then allowed to cool in a room with an air temperature of 20 degrees Celsius. The temperature T in degrees Celsius is measured every minute as a function of time m in minutes, and these points are plotted on the coordinate grid. It is found that the temperature of the water decreases exponentially at a rate of 25% every 5 minutes. A smooth curve is drawn through the points, resulting in the graph that is shown. And we are asked to first state the transformed exponential function in the form y equals a times c to the power b bracket x minus h plus k that can be used to represent this situation. So this is what we talked about yesterday. All right, so we're going to write our equation here first. And in that form, it asks us to do it in that specific form. So the first thing we can do is we can look at this graph, and we see that the horizontal asymptote is at 20. And that is because the temperature of the room is 20 degrees Celsius. So the temperature of the water will never get below that. Also, theoretically, it'll never get to be exactly 20 degrees Celsius. Because as it says, the temperature of the water decreases exponentially at a rate of 25% every 5 minutes. 25% of something will always be something. It'll never get down to 20. Okay, it's always being cut by 25% every 5 minutes. So you can see that we start at a temperature of 100 degrees, and after 5 minutes, which would be right here on the graph, the temperature will be 25%. It'll be cut by 25%, which means it would maintain 75% of its temperature. So at 5 minutes, it'll be 75% of 100 degrees, which will be 75 degrees. And then another 5 minutes, which is at 10 minutes, it would be 75% of 75 degrees, and so on. Okay? So because you're always taking 75% of something, there's always going to be something left there, and it's always going to be above 20 degrees. And that's why you've got that horizontal line there for y equals 20, which would be our k value. So as we start to build this graph, we can say that k equals 20 because that is where the vertical asymptote is. Normally, our exponential functions have an asymptote on the x-axis, the line y equals 0. But this asymptote is up 20 units. The other thing we can state is what our B value is. Our C value. Our C value is the growth factor. We've said before that if, let's say, bacteria are doubling, then the base C would be 2. If the number of bacteria is tripling, then the base C would be 3. If it's a half-life scenario where something is decaying by half of its amount every so often, then the base C would be a half. In this case, the temperature of the water is decreasing at a rate of 25% every 5 minutes, so therefore, the amount that's being maintained, as I said before, would be 75%. And so C, the base, would be 0.75. This is our growth factor. If you look at the graph, it has not been shifted to the left or the right. It's starting on the t-axis, and then it's decreasing. That's another reason why our base has to be between 0 and 1, because it's a decreasing function. And we got our base to be 0.75, so it fits that. And again, this graph starts on the t-axis, so therefore it has not been shifted left or right, so our h value will be 0. H equals 0 because there is no horizontal shift. So based on those 3 parameters, we can start to at least build our equation. It'll be y equals A. We don't know what A is. We're going to figure that out. C, we said, is 0.75. And we are going to have an exponent here. We do know that h is 0. So it'll just be exponent bx plus 20. That's what we know right now. And if we wanted to, we could change our parameters so that instead of y equals, T for temperature equals. And instead of x, we could use m for the number of minutes plus 20. Now I put a T there. Sorry, that should have been B. So we need to figure out what this exponent is going to be. And if we look at the graph up here, as well as what our general form of our equation is, that's on the formula sheet, A times B to the power T over P, what we can do is we can write it like this. We can write it like that as m over 5. Which means that our B value is 1/5. Okay, that's what it means. Now, where does that come from? Well, again, remember that this exponent, t over p, t refers to the time that has elapsed. P refers to we call it the doubling period, or we can call it the multiplication period. In this case here, we are told that the water temperature decreases by 25% every 5 minutes, or it maintains 75% of its water temperature every 5 minutes. And so because we started with our base being 0.75, our growth factor is 1/5 of the time that has elapsed. You see, if 5 minutes has gone by, then 5 divided by 5 is 1. That means it's going to drop by 75% only once, which it would, right? We're told that every 5 minutes, the temperature drops by 25%. It maintains 75% of its temperature. So if 5 minutes has gone by, 5 divided by 5 up here is 1. It'll have dropped by 25% one time. After 10 minutes, 10 divided by 5 is 2. It'll have dropped by 25% twice, and so on. So this tells us that this relationship is correct for the scenario. You take the number of minutes and divide it by 5, and that'll tell you how many times the temperature has dropped by 25%. Okay, so the B value here is actually 1/5. So there's our equation partially. The only thing we have to do now is figure out what our A value would be. And this is where we go back to our graph and we sub in a point that we know lies on the graph. And the only one we know for sure lies on the graph is its starting point, the point 0, 100. When the time is 0, the temperature is 100. So the temperature is 100 when m, the number of minutes, is 0. So subtract 20 from both sides, you'll have 80 over on the right side, and you'll have 0.75 to the power 0, because 0 divided by 5 is 0. Anything to the power 0 is 1. And so A equals 80. And now we have our equation. So the equation would be T, the temperature, so again, T, the temperature is 80 times 0.75 to the power m over 5 plus 20, where m is the number of minutes that the water has been cooling. So we can check to make sure that that equation matches the graph. If we open up our graphing calculator and we put this equation in there, 80 bracket 0.75, close the bracket, to the power x on 5, and then there's that plus 20 on the end. If we look at our graph, our window should match what is there. Okay, for time, just so we can clearly see the t-axis, I'm going to go from -10 up to, let's say, 120. And let's do a scale of 10. For my y values, I'll go from -10 up to 110. And again, a scale of 10. So there's that graph. And so to check this, if we look on the grid that we see here, after 20 minutes, the temperature should be about 45 degrees, halfway between 40 and 50 approximately. So if we go into trace mode and we let x equal 20, we get 45.3125, what we thought we'd get approximately. Okay. At 40 degrees, or 40 minutes, I should say, the temperature should be a little bit below 30 degrees. So if I let x equal 40, 28.00, and there's more decimals there, but it's just below 30 like we thought it would be. So we're just doing this as a check to make sure. At 100 minutes, it should be just slightly above 20 degrees, and it is. Okay, so we're just checking to make sure that our equation appears to match what was on the grid, so that's our check. So there's our equation. Okay. Describe how each of the parameters in the transform function relates to the information provided. Well, we've kind of already done that. We said, well, this is what K is and this is Y. C is 0.75 and this is Y. So we've already explained what those parameters, where they come from. Okay? So the next one, again, deals with a decay scenario. The radioactive element AM is used in household smoke detectors. AM-241 has a half-life of approximately 432 years. The average smoke detector contains 200 micrograms of AM-241. So we've got a graph there that shows the amount of AM-241 remaining. The half-life is 432 years. So it started with 200 micrograms, I should say. After 423 years, you'd be down to 100 micrograms, half of what you had before. So that's that point right there. That corresponds to 432 years. Okay, because that is the half-life. That's how long it takes for it to decay. So we want to say what is the transform exponential function that models this graph showing the radioactive decay of AM-241. So once again, we can write our equation by looking at some parameters. We don't know what A is. We're going to calculate what that is. But if we use this general form, y equals A times B to the power T over P, remember that B is the growth rate. And in this case here, the amount of AM-241 is being cut in half every 432 years. So B is 1/2. That is the growth rate. P is the growth period. And we're told that it cuts in half every 432 years. That is the p-value. This is the growth period. This graph has the t-axis or the x-axis as its horizontal asymptote. So there is no k value that's added on the end like there was with the last example. There is no vertical translating here. K equals 0 because the t-axis is the horizontal asymptote. So if we plug these in, we will have A for the amount of AM241 equaling A times B, which is a half, to the power T over 432. And if we use the initial point, 0, 200, we can calculate what A is. Again, I'm using the point 0, 200. 0 divided by 432 is 0, so 200 will equal A times 1/2 to the 0. Anything to the 0 is 1. And so A equals 200. And our equation would be A, the amount remaining, equals just 200 times 1/2 to the power T over 432. And if we look at that equation, right, this AM241 has a half-life of 432 years. When you let T equal 432, 432 divided by itself is 1. 1/2 to the 1 is a half. And a half times 200 is 100. And that matches this point we have right here. So in the last example, we used our graphing calculator to check. We can also just use the equation that we came up with. So let's check at T equal, let's say, 1800 years. When we look at our graph, 1800 years is right there. The amount remaining is just below 20. Maybe a little bit closer to 20 than it is to 0. Looks like it's a little bit higher than halfway between 0 and 20. So we know we should get something just slightly below 20 micrograms when T is 1800. So it'll be 200 times 1/2 to the power 1800 over 432. So we go to our calculator. 200 bracket 0.5 to the power 1800 over 432. Like we said, below 20, closer to 20 than it is to 0. 11.14 micrograms. Okay, which again matches what we thought it would be. Between 0 and 20, closer to 20 than it is to 0. And that's just a check to make sure our equation matches the graph. Okay, so we've identified where all the parameters come from, which is what part B asked. So for practice, we should do questions 6 through 8 on 355 to 354. We've got one more lesson to do on this chapter that we'll do tomorrow. And that's with solving exponential equations. And then Thursday will be your quiz on chapter 7. And then we'll start chapter 8, logarithm, functions next week. And then after chapter 8, that'll be our next exam. Okay? So this stuff generally is, most students find it to be easier, especially compared to the trig stuff. So do your practice, study, and you get a chance to bring your mark up. And I know that trig test was difficult, but this stuff is generally, most students find it easier, so definitely a chance to bring up your mark. So speaking of that trig test, we're now going to go through it.